Okay. Once again, good evening, everyone. I'm Anish Ambikar, PhD candidate at ISC Bangalore, and welcome to the weekly live interaction for Engineering Mathematics 2. The course code is NOC 23MA25, and today we'll be discussing some questions related to the concepts taught in the first week. Through these, the general format going forward would be as follows. We have some selected questions, carefully selected questions, which we'll be discussing and trying to solve here on these live interactions. And apart from that, if you have any doubts from the lectures, this would be the time to ask them. The aim here of these interactions is to help you get more engaged with the course and hopefully end up with like more satisfactory results at the end of this whole course. The weekly assignments that are posted usually there'll be, for example, the assignment one will be, I think it is due on 8th or 9th of Feb, so that won't be discussed here. We can discuss it only after the submission date because that falls under the evaluation criteria for NPTEL. With that in mind, let us begin. So here is our first problem. We are given f of x y z equal to x cubed plus y to the power 5. So can someone quickly comment what f is? Like, is it like a vector field, a scalar field? At the beginning, I think in the first or the second lecture, it was first lecture itself. I think scalar fields are covered. So this is part of scalar field. This is an example of scalar field, and we are asked to calculate gradient of f at a particular point p. So anyone wants
3i
to? Huh.
3i plus 12005j, I think.
So we calculate gradient of f. We'll arrive at the answer, but just a quick review. We calculate gradient of f. So this operator is called as Nabla-Ordel, and its value is essentially given as dou f by dou x I hat plus dou f by dou z dou f by dou y j hat plus dou f by dou z k hat. So the gradient function would take like a scalar field f and convert and give us a vector out of it. For this particular example, since f is equal to x cubed plus y to the power 5, we can calculate partial derivative of f with respect to x to be dou x cubed plus y to the power 5 by dou x, which is nothing but 3x square plus 0. So here there is no term involved because of y. Similarly, partial derivative of f with respect to y would be nothing but 0 plus 5y to the power 4. And f doesn't contain any term with z in it, so partial derivative of f with respect to z is 0. In this particular case, we are given the point P to be 1, 7, and 0. So we substitute x equal to 1, y equal to 7, and z equal to 0 in this equation. And therefore, we would get 3x squared to be equal to 3 times, which is nothing but 3, and 5y to the power 4 is nothing but 5 times 7 to the power 4. If you move this around a bit, this essentially becomes 7 square whole square, which is 49 square, and 49 square is 2401. So this is 12,005. So we basically end up grad of f to be equal to 3i hat plus 12,005 j hat plus 0k hat. So this is the first option. Okay. Anyone has any questions regarding the gradient operator, nabla order, or it is clear? Okay, I'm assuming it's clear. If not, stop me. Okay, the second problem is we are given a function r of x where going forward, one notation here that going forward bold letters would represent vectors. So we are given a vector function r of x which takes a parameter x by 1 upon x square minus 1 I hat plus e raised to x j hat plus k hat. And we are asked to find the values of x such that r is continuous. So this is an example of a parametric vector function with x as the parameter. In the lectures, I think the professor has covered certain examples with t as the parameter, but here it's just x, and we are asked to talk about the continuity of this r of x. So, does anyone remember the definition for continuity for a parametric vector function of this particular type? So, if you want to check its continuity, we need to see if I think there are three conditions involved. Firstly, r of x should be defined in yes,
Individually, we have to check that component of
yes,
vector field that continuous or not.
correct, correct. So the conditions that I'm writing down, we essentially have to check if for r of x continuity at x equal to a, we have to check this for all three components. And first we need to see if the vector function r of x is defined in the neighborhood of a. Secondly, we need to check if limit of r of x extends to a exists. And the third thing is this limit itself should be equal to the function value, which is so together these three conditions applied to or like checked for all the three components would give us continuity. Straight away we can see that r of x has three components. We'll start from the jth component. So sorry, for the z component, which is 1 into k hat. One is independent of x. So basically for this particular case, we could have x belonging to the entire real, all the real numbers, and still the z component is defined. The next is the y component. Y component is e to the power x j hat. Again, e raised to x, if you remember, is defined for all real values. So a graph of it would look something like this. Y is equal to e to it intersects at 0, comma 1. And it's defined for all x. So like, hence x can cover the entire real line. The third is the x component, which is 1 over x square minus 1 I hat. Now you can see that this will have some problems, specifically if you factorize the denominator. X square minus 1 can be factorized as x minus 1 into x plus 1. So the denominator x square minus 1 will go to 0 when x is equal to plus minus 1. X square minus 1 goes to 0 when x is plus minus 1. Therefore, the x component is not defined for x equal to plus minus 1. But it can be defined for all other x. So Essentially, if we look at this, would be defined for x belonging to R, excluding -1 and 1. So if you look at all z, y, and x component, the range of values which x can take, and take a common intersection of all the three domains, then we essentially end up with x can belong to the set of real numbers, excluding -1 and 1. Okay, this I've written it in a more simplistic manner, but we could essentially plug this 1 over x square minus 1 term and check the conditions 1, 2, and 3. And we will see that it might be defined for in the neighborhood, but this limit itself will not exist, neither will the value at x equal to plus minus 1, which would tell us that the function is not continuous at x equal to -1 and x equal to plus 1. Okay, the third problem, we are given a surface with the equation xy plus f of xyz equal to xy plus y cube plus z. This is equal to 0. And we are asked to find the unit normal to this surface at point P, which is defined by the coordinates 1, 0, and 0. Does anyone remember how to do this?
Simply find gradient of that scalar field
Correct,
at given point
correct.
and take unit normal.
So if we have level surfaces like this one, so f of xyz equal to 0 or f of xyz equal to c, then we can calculate the unit normal simply by calculating gradient of that function f at the particular point P, which is nothing but dou f by dou x at P plus dou f by dou y at P j hat plus dou f by dou z k hat. And in this case, the partial derivative of function f with respect to x is nothing but y cubed by dou x dou of z by dou x, which is equal to y partial derivative, and then I'll calculate by dou x at point P, which is nothing but 1, 0, 0. This will be essentially 0. So dou f by dou y is nothing but, I'll just write down the answer here, x plus 3y square plus 0. And if I am to calculate dou f by dou y at point P, it ends up as 1 plus 3 times 0, which is 1. And dou f by dou z is 0 plus 0. First two terms do not have any z component in, and 1. So the partial derivative of f with respect to z is always constant, equal to 1. It won't depend on the point. And therefore gradient of f at point P would be given as 1 j hat plus 1 k hat. Now if you want the unit normal, we'll just simply divide the gradient vector with its normal with its magnitude, sorry. So you have 1 j hat plus 1 k hat. The magnitude would be 1 square plus 1 square, which is nothing but 1 by root 2 times j hat plus k hat. So this would give you your unit normal n hat to surface f of xyz equal to 0 at point P given by 1, 0, 0. So option B. Have you guys understood the proof of how we get to the how we get gradient as the normal to a surface?
Yes, sir.
Yes, sir.
Okay. The
Is
fourth,
conservative.
sorry,
Is it a third problem that answer conservative equal?
uh, I'm, I'm unable to hear it. Can
Can we
you?
call that conservative? Can we call that answer is a conservative of potential field like surface?
Okay, you want to know if this is conservative, is it? The function f of xyz, right? This is given a surface, so the function f of xyz is zero everywhere. So no matter if we move from one point to another point, like if we look at, suppose you have some vector field. I'm just drawing a random representation, some sort of vector field. We'll call it. We'll be calling it conservative if whether, and we are moving from point A to point B. We'll be calling it conservative if the path integral from point A to point B is independent of the path, right? So in this in this case, actually the entire surface is, if you take the vector v is equal to grad of f, right? And then you perform a integration from point A to point B. In this case, the entire surface itself has this value f of a equal to f of b equal to 0, right? So it doesn't matter if you, like, it's not even dependent on the points in a sense. If a, b are like here and here, or if you have say a and c between here and here, then the path integral will always be 0. It's
Yes,
it's
sir.
like it's an interesting question because it falls slightly in between, in the sense that the surface is always 0. So no matter what work we do, whatever path we take, it will be always 0 and independent of that. But at the same time, it's not even dependent on the points themselves. So you could have the points next to each other, or you could have them like a very, very large distance apart, but you would always end up with 0. No, conservative would mean that, okay, conservative would mean that it's not dependent on which path you choose, right? So, but another way to also define it is, suppose you start from a point A and end at the point A, and say take any path to do so. If the
Yes,
vector
sir.
field is conservative, then it will be 0.
F is equal to FB, so
Uh,
it
yes,
will be zero.
yes. Suppose like gravity, in case of gravity, you start from, say, from bottom, then you move to couple of, you you have like a ball from bottom, you throw it up and catch it back, and then calculate the work done by gravity, that would be 0. Or if you like throw a ball across the ground like a projectile, so whether it moves like this or it moves like this, and if this is your z-axis and gravity is acting like this, in these cases the work, like, since it ends up at the same z-axis or the ground level, the work done would be 0. But if you, on the other hand, consider the case of air friction while throwing the ball up and down, then while going up, air friction will act downwards, while when the ball is coming down, air friction will act upwards, and therefore it will always oppose the motion, and work done by air friction would be non-zero. So that would be like an example of a non-conservative field, or friction, again non-conservative. Problem number 4, we are now again given like a parametric vector field r of t, and we are asked to calculate dr by dt at t equal to 0. So before I actually solve this, what do you think this r of t, what kind of path this r of t traces out in space? I'll draw an X. What do you think this would trace out in space? If we take the simple case of t equal to 0, then r of 0 would be 1 I hat plus 0 j hat plus 0 k hat. So this is where it would be starting, and then it would be rotating like this, but also moving upwards along z axis. So it's essentially like a helical path that this vector field would trace if we consider the parameter t to be time. And then we want to calculate the tangent to this vector field. That would be nothing but partial derivative of each of the components. So cos of t I hat plus d by dt of sine of t j hat plus d by dt of t square k hat. So derivative of cos is minus sine, derivative of sine is cos, and of t square is nothing but 2t. So if I just plug in t equal to 0, I'll get first value is 0, second is 1, third is again 0. Right, so we'll get this as the tangent to this particular parametric vector field, and from this geometric interpretation we can also see the same, that the point will start to move in this particular direction. So the tangent should be something along these lines. The fifth problem, we are now asked to calculate a tangent plane at the point 0, 0, 0. So P is 0, 0, 0, and the surface is f of x, y, z is equal to x cube plus y cube minus z equal to 0. I'll just rewrite it as x naught, y naught, z naught. What is the equation of the tangent plane? Does anyone remember? Okay, so the tangent plane is essentially, if this is my surface and this is my point P naught, and this is another point P, then on the surface, my normal to the surface is given by grad f at point P naught, and if the point P has coordinates x, y, z, P naught has coordinates x naught, y naught, z naught, then the tangent plane is given by this relation that my normal will always be proportional to any line drawn on the tangent plane. So we would have grad f at P naught dot x minus x naught, y minus y naught, z minus z naught. So this is our representation of like the two vectors being orthogonal to each other. If I calculate quickly grad of f, it would be nothing but dou f by dou x, which is 3x square I hat, plus dou f by dou y, which is 3y square j hat, minus 1 k hat. I substitute now my values. This is nothing but 0 I hat, 0 j hat, minus 1 k hat. I now use this and substitute it in this general equation for the tangent plane, and I would end up with 0 into x minus x naught plus 0 into y minus y naught plus minus 1 into z minus z equal to 0. Again, x naught, y naught, z naught are 0, 0, zeros. They are the point p naught. So I end up with 0 plus 0 plus minus 1 times z minus 0. So minus z is 0 or z. This would be my tangent plane to the surface f of xyz at the point 0, 0, 0. Okay, any doubts here? If not, we'll move to the next one. We are now given a vector, so r of xyz. This essentially becomes a vector field, and we are asked to check if this is conservative or not. So how do we do that? Does anyone remember? Okay, so the simplest way is to assume some sort of underlying potential. So we assume underlying potential phi of xyz such that grad of phi is equal to r. Therefore, we would have dou phi by dou x is equal to x, which we can integrate to get x square by 2 plus some function g of y comma z. Next up, we'll differentiate this function. The partial differentiation of this function with respect to y, which is nothing but dou g by dou y. X square won't contribute, and this should be equal to y square. Therefore, g of yz can be written as y cubed by 3 plus some function h of z. Since we are taking partial derivatives, we need to account for h function of z. Assume some function of z is there. This would give us phi to be x square by 2 plus y cubed by 3 plus some function h of z. Next up, we take this function and take its partial derivative with respect to z. X square term won't contribute, y cube term won't contribute, so we simply have dh by dz. This should be equal to z square. Therefore, we get h of z to be equal to z cubed by 3 plus some integration constant. Substituting this here, we essentially end up with a potential of the form x square by 2 plus y cubed by 3 plus z cubed by 3 plus c. If this is our underlying potential, then r equal to grad phi ends up to be xi hat plus y square j hat plus z square k hat. Right, so we are able to show that the given vector field by assuming an unknown form of underlying potential that there it does indeed exist, thus our vector field is conservative. Apart from like this method, are there any other tests or method using which we can determine if R is indeed a vector field? Okay. Another way to do it would be to suppose R has components Rx, I hat, plus Ry, J hat, Rz, K hat. Then another, like a second method would be if R is indeed gradient of a underlying potential, then the second method would be the Rx would be checking if these are indeed if these relations are indeed satisfied. If these three relations are indeed satisfied, then also we can say that R is a vector field. So if we just quickly check, we can see that the first equation is basically 0 equal to 0. Second equation is again 0 equal to 0. And so is the third one. So using both the methods, we can confirm that indeed the vector field R is a conservative vector field. The next problem is we have been given a vector field f of x, y, z, and we have been told that it is indeed conservative. And now we want to find the underlying potential for this particular field. Again, we'll proceed with the same method. Like the first method, we'll assume phi of x, y, z to be underlying potential. This essentially means that grad phi is equal to f. So dou phi by dou x should be equal to 2xy square z, which would mean that phi is nothing but integral of 2x, integrating 2x y square z dx, assuming y and z to be independent functions, plus g of y comma z, which is nothing but x square y square z plus g of y z. Then we take the partial derivative using this form into y. So dou phi by dou y, which we are given to be, which from this expression comes out to be x square 2y z plus dou g by dou y. And from the equation, from the problem, we know that this is equal to 2x square yz, which essentially means that partial derivative of g with respect to y is 0. Therefore, g of yz is nothing but it will simply be a single function of z, a function of a single variable z. Then we substitute this thing into here. So, and we calculate the partial derivative of phi with respect to z, which turns out to be x square y square 1 plus dh by dz, which is equal to x square y square from the problem. Therefore, partial derivative of h with respect to z is 0, which means that h of z should be a constant. Combining all this information, we end up with phi of xyz to be equal to x square y square z plus some constant c. So that is option number D. This is clear, right? Okay, so if there are no questions, we'll move to the next problem. Problem number 8. We we are given a statement and we are asked whether it's true or false. The statement is let vector field F is defined as, so this is a vector field minus x I hat minus y j hat plus 2z k hat, and we are asked to comment whether this field is solenoidal or not. So if we want to say draw it, okay, drawing it in Z would be hard. I'll just first show how it looks in x and y. So if this is basically the z plane, sorry, xy plane, or z equal to 0, you would essentially have something like this. You would essentially have something like this, a field which is pointing towards origin, and its vector values get moved, like a radial inward field. And this is along, like, for the xy plane, and then you would also have another component for z. So that would be, say, like pointing outwards or pointing out of the plane or into the plane, depending on and proportional to the magnitude of the z coordinate. So solenoidal. So anyone remembers the definition of solenoidal?
If dot product with the vector field is 0, then we can say that the vector field is solenoid.
Yes. So this is for solenoidal. And what this grad dot f, this is essentially called as divergence. So what does divergence mean in a physical sense? So in a physical sense, divergence essentially means, if suppose I draw like a unit, a very small volume element at a particular point, and I want to see if, like, whatever the vectors are, they are like compressing in or expanding out of the field, like what is the flow inside and out of the box, total flow inside and out of the box. That is what, in a sense, divergence means. So it's a measure of expansion or compression, in a sense, the of the vector field. So from this particular diagram, if we look at only the z equal to 0 plane, it seems like it's all coming inside. But if I try to draw it, it's very difficult to draw it in this XYZ space. We'll just directly calculate this. So this is nothing but dou f by dou x plus dou f by dou y plus dou f by dou z. Dou f by dou x is nothing but -1. Dou f by dou y is nothing but, again, -1. Sorry, dou f x by dou x, dou f y by dou y, and dou f z by z. I'm representing the components of vector f as fx I hat plus fy j hat plus fz k hat. So this is essentially partial derivative of minus x with respect to x plus partial derivative of minus y with respect to y plus partial derivative of 2z with respect to z. So we end up with -1 plus -1 plus 2, which is nothing but 0. So grad dot f is 0. Therefore, this vector field is solenoidal. So the statement becomes false. Okay. We now move to the next problem. We are given surface f of scalar field f of x, y, z equal to x plus y plus z minus 3, and we are given a point 0, 0, 0, and we are given a direction vector b is equal to I hat plus j hat plus k hat. Straight away, before, and we are asked to calculate directional derivative of f in the direction of b. This is what we are asked. Straight away, we can see that magnitude of b, which is 1 square plus 1 square plus 1 square, which is root 3, is not 1. So we reduce b to unit vector, which is nothing but 1 by root 3 times I hat plus j hat plus k hat. Now to calculate the directional derivative, first we have to calculate gradient of f, which is nothing but I hat partial derivative of f with respect to x, which is 1 I hat partial derivative of f with respect to y j hat partial derivative of f with respect to k hat. It's 1 j hat plus 1 k hat, right? And if you now want to calculate point P, that is nothing but gradient of f at point P dot b hat, but gradient of f itself is independent of points of any point xyz, so it will always be this particular value. So I got 1 I hat plus 1 j hat plus 1 k hat dot 1 by root 3 times I hat plus j hat plus k hat I hat, so it's 1 plus 1 plus 1 by root 3. It's nothing but 3 by root 3 equals root 3. Okay, so this gives us directional derivative at the given point for the function in the given direction. And this is the final problem for the day. We are given a vector field a of xy to be 2xy minus x square minus 1 I hat, and x square plus y square j hat. So we are in 2D plane and we are asked to calculate line integral of a along the curve c. So it's a closed line integral over the curve c, which is closed by these two particular functions. So in xy axis, if I draw it, both the curves do pass through 0, 0, and x equal to y square would look something like this. X equal to y equal to x cube. This is, sorry, this should be going like this. This should be a parabola. This is my function y equal to x equal to y square, and I'm given another function y equal to x cube, which would look something like this. With y equal to x cube, we can easily calculate the intersection point. It's 1, 1, but if you want, it would be like y is equal to x cube and x is equal to y square. Therefore, if I just substitute y square here, it would be, or if I substitute this y equal to x cube here, it would be x is equal to x cube whole square. It's nothing but x to the power 6, so x6 minus x equal to 0. x times x5 minus 1 equal to 0. This has two solutions, x equal to 0 and I should use the word real solutions, x equal to 0 and x equal to 1, which would give us the two intersecting points. So our overall curve C would be, say, something like this. It has two parts, C1, C2. C1 is follows y equal to x cube from 0, 0 to 1, 1, and C2 follows x equal to y square from 1, 1 to 1, 0. And curve C is essentially C1, that's C2. Okay, and now we are asked to calculate the line integral. So the way to do this, I'll just clear the ink here. Yeah, to do this is 0, 0, 1, 1, y equal to x cube C1, x equal to y square C2, and A. So before we go on a lengthy integration spree, can someone quickly comment if A, since this is a closed loop, if A is conservative or not? Because if A is conservative, then our answer should automatically become 0, right? Because it's a closed curve. Does anyone know if this A is conservative or not? Or how can we find that out? So if we want to check if A is conservative, we'll let we'll say that let A is equal to grad of phi.
I think it's conservative, sir.
It's conservative, is it? So how do we test that out? We check dou Ax by dou y if this is equal to dou Ay by dou x, right? This is Ax, Ay, dou x by dou y is nothing but 2x, and dou Ay by dou x is also 2x, right? So if it's conservative, then our whole problem is solved because we are essentially moving through a closed loop like this, and yeah, we are moving through the closed loop ending at the same point, and therefore the path integral ADR would be nothing but, I'll just split it into two terms, A dot dr C1 plus A dot dr C2, which is nothing but grad phi dot dr C1 plus grad phi dot dr C2. I'll label this point as P1, this point as P2. So you have phi of P2 minus phi of P1 for this particular term plus phi of P1 minus phi of P2 for the second term. This will just cancel out each other and we end up with 0. If you want to calculate the underlying potential, we can do it by dou phi x. Dou phi by dou x is equal to 2xy minus x square minus 1, and dou phi by dou y is equal to x square plus y square. I'll use the second equation to begin with. For my phi will be equal to x square y, it's y cubed by 3 plus some function g of x. Now I put this potential function value in this particular equation to get dou phi by dou x is nothing but 2xy plus 0 plus g of x. It should be equal to 2xy minus x square minus 1. Therefore, g of x is nothing but minus x square. Sorry, dou g by dou of x. Sorry, forgot differentiate. Yeah. Therefore, g of x is nothing but minus x cubed by 3 minus x plus c. So my underlying potential phi of xy is nothing but x square y plus y cubed by 3 minus x cubed by 3 minus x plus c.
So,
So,
sir, if
mm,
the path is closed,
mm-hmm,
then the integrand will be always zero, right?
mm-hmm. Yes, for this particular case, it will be always 0.
Okay.
So it won't matter if this is the path or this is the path,
Mm.
or say like a box is a path. But
Okay.
like this is the smart and probably less involved way to do it. The other way and probably the more straightforward way would be to just do this whole integration first for C1 and then for C2. The curve C is nothing as we discussed A dot dr over C1, A dot dr over C2. And in this particular case, if you want, I can show this to you as well. But in this particular case, what happens is both the individual paths are also 0. So that can be confirmed directly by looking at phi of xy also. If you just put x equal to y equal to 1, then so phi of 0 0 is c and phi of 1 1 would be 1 plus 1 by 3 plus 1 by, let's write it here. Phi of 0 0 would be equal to c, phi of 1 1 would be equal to 1 plus 1 by 3 minus 1 by 3 minus 1 plus c. This is also,
Let's see.
so the point 0 0 and 1 1 in a sense are equipotential.
Mm.
So what we could, another thing we could do, but is like if you take this particular path, it would still be 0, or path like this would be 0.
Okay, sir.
Okay, so that covers up the problems that I had planned for this particular week based on whatever professor taught for the first week. Do you have any other like doubts that you have?
No, sir. But I want that. Can you give me that the real life application of this vector,
Of
whatever that the call and divergent and the line integral, all
mhm.
this.
Okay. So are you guys familiar with uh, are you guys familiar with conservation of mass? The concept of conservation of mass. So okay, suppose you have, we'll start first with divergence spread dot v. Okay. Suppose you have like a fluid, say like water flowing through a pipe or something like that. So what we essentially do is one way to apply conservation of mass is we say that mass essentially cannot be created or destroyed. So what we do is we take a small box element in the fluid and we have some velocity field, some vector field v of xyz, which denotes the velocity of this fluid. And now if we calculate the amount of fluid which is flowing into, so this is the fluid flowing into the volume element, and this is the fluid flowing out of the volume element, and we essentially keep on shrinking this down till we reach like a point, say p of xyz. Conservation of mass would essentially be written as divergence of velocity field to be equaling 0. On the top of my head, this is the one example that I can think of. And the way you could say prove this is, you suppose this is my point p of xyz. I'll just stick to two dimensions for now, p of xy, and this is an element of say size dx by dy. This is my fluid flowing in and fluid flowing out. Then the amount of mass that is coming in is given by rho times A. You could also have some fluid flowing like this also. So rho times, this is dy, right? Rho times dy times velocity of x minus dx by 2. Okay. Okay, so the fluid that is coming from the left hand side, if I write v has components vx I hat plus vy j hat, right? The fluid that is coming inside will have velocity vx minus dou vx by dou x into dx by 2. So it will be rho into rho density into area into velocity is the amount of mass flowing inside minus the amount of mass flowing outside. So this is the right phase, plus you write similar equations for fluid coming in from the bottom half, fluid going out of the top half. So rho vy will cancel out, rho vx will cancel out, and this whole thing should be equal to 0, which essentially says that whatever fluid is coming in from the left and the fluid which is coming in from the bottom should be equal to whatever fluid is exiting out of that particular, there's small mass. Vx terms and vy terms will cancel out. So you will end up with minus rho times dou v by dou x into dx into dy minus rho times dou vy by dou y. These two terms are here, these two terms are here, into dy into dx. This should be equal to 0. I remove the rho and I also divide by dy by dx and shrink this whole volume so that dx and dy both go to 0. Then my equation would end up looking like dou vx by dou x plus dou vy by dou y. This is equal to 0, which is nothing but gradient of V, grad dot V is equal to 0. So one way to write conservation of mass for a fluid would be in terms of checking if the fluid is incompressible, like its density is constant. For example, in case of water flowing through the pipe, you can assume it is incompressible, it has the same density equal to 1 gram per cc. One way to write that equation analytically is divergence of the velocity field should be equal to 0. This is for divergence, and curl essentially tells you about rotation. Like if if your vector field is like rotating about a particular point. Okay then.